Hello, we are going to continue where we left off from part one. So we are in our 1.5 notes looking at polynomial functions and complex zeros. We did the first page front and back, and now we are at the quick notes section. So for number one, if a factor is quadratic, imaginary zeros or solutions can be found with the quadratic formula. We can then write the functions or the function, that should not have an S there, as a product of n linear factors if we have an n degree. And we actually saw this in example one. So on the very front of our notes, that is where we did that. We could not factor that quadratic, so we used the quadratic formula, and then we were still able to write it in factored form. So feel free to flip back and remind yourself what example one was. The second thing, we're looking at multiplicity. So I'm going to pull up a slide real quick to show the difference in the multiplicities. These two graphs were the exploration we did on the previous page. So I rewrote the equation from number one, and I wrote it as x minus 2 squared. So I have this 2 here, and then in my other graph, I have a 3. And so my graph acts differently depending on the exponent on that factor. At positive 2, when my exponent was 2, it bounced back and looked like a quadratic. At positive 2, for my factor x minus 2, when there was a 3 exponent, it looks like a cubic. It hits the x-axis, kind of hovers, and then continues through. And so that's what we're talking about when we talk about multiplicity. So let's go back to our notes. Multiplicity is the number of times a factor occurs. And so if I have a function that's like x minus p to the power of k, I would say p is a 0 with multiplicity k. And I'm going to actually do an example with real numbers. So if I had x minus 3 squared, I would say 3 is a 0 or an x-intercept with a multiplicity of 2. And so in our table here, we're going to specify if our multiplicity is an odd number. So if k is odd, our graph passes through our x-axis. So I'm going to do a little sketch. If k is 1 is an odd number, it's going to go straight through. There's my intercept. There's no hovering. It's a clean piercing straight through the x-axis. If I have a multiplicity of 3, while it still goes through, it has a little resistance. So it's going to hit the x-axis, hover a little bit, and then continue. So there's, I should have used a different color. There's almost like a horizontal-ish piece before it continues. And it could come down the other way. It doesn't necessarily have to be increasing. So it could come down, hover, and then continue, something like that. So you have 2 examples for a multiplicity of 3. On the other side, if k is even, that is where we have a bounce. So it will not go through the x-axis. So if k is 2, our graph is going to hit the x-axis, change direction, and bounce back up. So in even multiplicity, it will bounce. In odd multiplicity, it does go through. And then they look slightly different as we get higher and higher in our multiplicities, but this is a good start of understanding of what multiplicity is. So we're going to look at a couple examples here. So example 2 says a polynomial function f has degree 5. So that means right now there should be 5 solutions. My degree is the total number of solutions I could have that includes real and imaginary. So I have a degree of 5 whose coefficients are real numbers and has zeros of x equals 2, 3i, and 1 plus I. Find the remaining zeros. So right now I have 3 solutions, so I am missing 2. Well, I notice these 2 are imaginary, which means if I go back to the front of my notes, using my conjugate root theorem, they have to come in pairs. So if positive 3i is a solution, I also know negative 3i would be a solution. And if 1 plus I is a solution, I would also have 1 minus I. Notice that I did not change the sign on the 1. I'm only changing the sign of the part with that imaginary portion. So yes, the 3 turned negative for this one because it's connected to the imaginary portion. Here, just the imaginary portion turned negative, but the 1 stayed exactly how it was because it was positive here. Example 3 says find a polynomial function g of degree 6 whose coefficients are real numbers and has zeros of x equals 4 with a multiplicity of 2, 5i, and 2 minus I. We're going to assume a equals 2 for the leading coefficient. So I'm going to start by writing it in factored form because I want to find the actual function. I'm not just finding the remaining zeros. So I would have, let's say, g of x equals, I know my leading coefficient is 2, so I'm going to start with that, and I'm just going to check that off my list. Then I also know I have a 0 at positive 4. The factored form would be x minus 4, because if I set this equal to 0, I get positive 4. A multiplicity of 2, looking back up here, means I would have an exponent of 2 on the outside of my parentheses. So I got that one. I also have a 0 at 5i, so I want to do x minus 5i, but that's imaginary, so I know it comes in pairs, which means I would also have x minus a negative 5i or plus 5i, because minus and negative turns positive. And then I have 2 minus I. So I'm going to do x minus 2 minus I. And again, this is imaginary, so it has to come in a pair. X minus 2 plus I. My 2 does not change, but the imaginary part changes sign. So this was minus I, so now this is plus I. So I checked that off my list. So I want to double check a couple things. If I have a degree of 6, I should have 6 solutions. So I have a multiplicity of 2 here. So this is 2. This would be 3, 4, 5, 6, because each of these just have an invisible 1 exponent. So that works. That would be my function of g that fits those characteristics. It doesn't say to simplify it, so I'm going to leave it exactly like that. All right, the bottom one, looking at number 4, it says complete the following. Find a polynomial function f of degree 4 whose coefficients are real numbers and that has zeros 2, 2, negative 3i plus I, and we're going to assume that a equals 1 for the leading coefficient. Once we have it, we can graph it and analyze the characteristics. So starting with part A, I am going to do the same thing I started with in part 3. So if you want to pause the video, try this one on your own, and then restart it, and I'll go through my explanation. So I have f of x. I know my leading coefficient is 1. That's what it tells me to assume. And then in factored form, I would have 2 as a solution, but since there's 2 of them, I can do a multiplicity of 2 by just writing it with an exponent of 2 instead of writing it twice. So that takes care of both of those. And then I would have x minus negative 3 plus I. And as of right now, I only have 3 solutions. I have 2 here and 1 here, but a degree of 4. I should have a 4th one. My imaginary solutions have to come in pairs. So my second one would be x minus negative 3 minus I. So that would be my function. Now, I cannot graph that because I have imaginary solutions here. So for part B, I actually need to simplify my factored form in part A. So I'm going to multiply some things out. I'm just going to do it underneath. So I'm going to leave that alone. And I just want to multiply these two. So I have x squared, and then I would have minus negative 3 minus I x. And then I would have minus negative 3 plus I x. And then my last would be this imaginary times this imaginary. Negative times negative would be positive. So plus, and then I'm doing, I ran out of room. Negative 3 plus I times negative 3 minus I. I'm so sorry for the space there. So that looks gross. So I'm going to simplify it even further. I'm not going to write the 1 anymore because we know if I don't include it, it's still there. So I have x squared. And then I'm going to distribute this negative in. So negative would be plus 3x because it's also getting multiplied by x, and then plus ix because negative times negative is a positive, and then ix. Same thing here, negative would be plus 3x because I'm multiplying both of these by x, and then minus ix. And then here, negative 3 times negative 3 is a positive 9, plus 3i minus 3i, so plus 3i minus 3i minus I squared. Woo! This is not for the faint of heart. I'm going to go up a little bit. I still want to simplify this, so I want to look what I have here. Plus 3i and minus 3i will cancel, so those go away. A positive ix and negative ix will go away. And then I squared I can rewrite as negative 1. So I would have minus a negative 1, which would be a plus 1. So here I have x minus 2 squared, x squared plus 6x, because I'm combining 3x and 3x. This is a positive 1 now, and 9 would be plus 10. This looks a lot better, and I can actually type this into my calculator now to see what the graph is. So let me grab my graphing calculator. So in my y equals, let me do it on this side, it's a little bit brighter. I have x minus 2 squared, and then my second set of parentheses, x squared plus 6x plus 10. And then I am telling you what the window should be. So let me change my window right now. My x min is negative 5 with a max of 5. Y min and y max is 60. So this is my graph, and I actually want to try to figure out what this y-intercept is. So I'm going to calculate, so second trace, my value. So I'm on option 1 when x is 0, and it tells me that y is 40. So on my graph, I know that it's going to hit 40, and then I have an x-intercept at 2 with a multiplicity of 2, which is why it's bouncing back off the x-axis. So my graph kind of looks something like this. And then I know that's not as accurate, but I don't want to mess up the writing that I have there. So I have my graph. And then for part C, I want to analyze the characteristics of the function. So for this, there's lots of characteristics we could do. We could look at concavity, increasing, decreasing, max, mins. I'm just going to do my relative max or mins, so my relative extrema and my absolute extrema. So my relative min, my relative max, and then my absolute min. I do not have an absolute maximum because my graph will go up forever. So my absolute minimum is at 2, 0, which means the y value is 0. My absolute minimum y value is 0. My relative min, so in my graphing calculator, I did second trace, and I want to calculate my minimum. I have one over here. So left bound, I'm going to go just slightly to the left of it, hit enter. Right bound, slightly to the right of it, hit enter. And then guess, I hit enter again. And I want the y value for this relative minimum. So 23.954. So my relative min is 23.954. And then my other relative min is at 0, which is also my absolute min. So I'm actually going to just leave it as my absolute. And then my relative max, let's figure out that one. So I want option 4. Left bound, so just to the left of it. Right bound, just to the right of it, and then guess is enter. My y value is 45.858. So 45.858. So I have some characteristics for my function. We're going to look at one more example just until we get like a barrier in our notes. So let's go ahead and flip, and then we're going to look at example 5. So example 5, here it says the graph of a 6th degree polynomial y equals j of x is shown. Identify all the zeros and state their multiplicity. So we're doing it just from the graph, and I realize the numbers are really bad. We can't really see the numbers here. So this is at positive 5. This is negative 5. So I'm going to say 1, 2, 3, 4. And then 1, 2, 3, 4, 5. So that's as evenly spaced as I think it can go. So all of my zeros, I have one here at negative 3. So I'm going to say x equals negative 3 with a multiplicity of, if it goes straight through, it's a multiplicity of 1. My next one is at an x value of positive 2. That has a multiplicity of 2 because my graph hits the x-axis and bounces back. It changes direction. And then my last one is at an x value of positive 5, and my multiplicity is 1. It goes straight through. There's no like hovering for it to be a multiplicity of 3. So does this function have any imaginary solutions? How do you know? So what we want to look at is if I have a 6th degree polynomial, I should have 6 solutions. Right now, I have 4 because I want to take into account my multiplicity. So I have 1, 2, 3, 4, so I'm missing 2. So we're going to say yes. Oops, because we have 4 real solutions. There are 6 total. Since our degree is 6. This means there are 2 imaginary solutions. Which also makes sense because if we didn't take multiplicity into account and we thought there were 3, there cannot be 3 imaginary solutions because they have to come in pairs. So there can only be 2 imaginary solutions or 4 or 6 because they have to come in pairs. So we are missing 2 imaginary solutions because we found 4 of the real ones. And this is where we're going to stop for part 2.